Hi everyone, I'm back again with problem 25 because I realized your book actually used the limit laws, and when I just was talking about this, I had sort of a different idea that also works. So I thought, why don't I explain that idea to you? Okay, so let's first do this part. So I'll copy this. So we're supposed to prove that, let's see, over here, myself some room. So we have a sequence of complex numbers, z1, z2, z3, etc., and they're going to limit to some complex number z. Okay, and we want to show that the associated sequence of real parts also converges to the real part of this limit. Okay, and so you can think about this like if this was our picture in the complex plane, and here's z, the limit, and there's infinitely many, all in there, or like basically all the z sub n's are in there. Then you can imagine this is in the complex plane, and so down here, just every single number has a real part, a real part, a real part, a real part, and then z also has a real part right there. The real part of z. This is maybe the real part of z2. Here's maybe the real part of z3, etc. And so we want to show that this sequence converges if we assume that this one does. Okay, so how do we prove that a sequence converges? Well, choose D positive. We need to show that we'll be eventually within D. We need to show that there exists an n such that past that point we have what? Well, all the real parts are within. What's our sequence? It's the real parts of the z's are within D. You know, they're D close. The distance between these things is less than D. Okay. But once we choose this positive number, then we know that this converges. We're allowed to assume that's true, and so we know there exists some. Okay, I'll call it something else. N tilde with n past n tilde implying that the z sub n minus the z is less than d. That's what we got to assume. We got that for free. The existence of this n tilde was given to us by assumption. Okay, and now will this do it? Well, yeah, because the zn minus z is really just equal to what is it? The real part of zn plus I times the imaginary part of zn, and then z is really the real part of z plus I times the imaginary part of z, and that is, let's see, less than or equal to real part of zn minus real part of z plus the imaginary part of zn minus the imaginary part of z. Let me think, is that correct? Yeah, I think so. So how do I see that? Well, it's just sort of a triangle. It's triangles, I think. That somewhere in the plane we have these 2 points, zn and z, and this is their distance, which is up here, and by the triangle inequality, you know, this real part distance is that horizontal length, and this imaginary part distance is that vertical length. And so, you know, this hypotenuse can only be shorter. It can't be shorter to first go over here and then up there. That's longer. Okay. Anyway, however you understand this, it is because of this triangle inequality. Okay, so now does that mean that we're okay? Well, let's see. Oh, yeah, okay. So I don't know about this. This was sort of I was just sort of thinking about this because I wasn't sure what to do next. So now let me move this over here, that pretty clearly from this triangle, that line length here is less than that one. So what we have is that the real part of Zn minus the real part of Z distance is, in fact, less than or equal to this distance, just from triangles. So is less than or equal to Zn minus Z. But then we were assuming that we already have that from assumption that on this convergence, if we're past n tilde, then this thing is less than d. So take n equal to n tilde, where the n tilde was guaranteed from the assumption that this converged. And then we're done. Now let me look back and see if this makes sense, that I've written something that makes sense. Okay, assume this, prove that this. Choose D, okay. Now what do I need to do? I need to show that there exists an n such that this is true whenever we go past that capital N. Well, we know that there's an n tilde such that going past the n tilde puts us there because of this. And maybe I'll even add that, because Zn converges to Z is what we assumed. Then I might write, but that thing is less than that thing, which then is less than D, and we're done. So just take n equal to n tilde. Okay, and then as you can see, like, this was just the real part. Clearly the only thing different is just the imaginary part. It's just the other side of that triangle. So the same argument, so I'd say then same argument shows that the imaginary parts of the Zn converge as a sequence to the imaginary part of Z. There's really no difference at all. So hopefully you understood this. If not, pause and think about it. Make sure you understand the logic and why I wrote the words in the order that I wrote them proceeding down. Okay. All right, so then we are done with half of it. We still need, because it asked us to do if and only if, that means we have to now assume the other way. So now let's assume. Okay, so maybe I'll change color. Now, assume the real parts of the Zn converge to the real part of Z. So assume that, and that the imaginary parts of the Zn converge to the imaginary part of Z. Want to prove that the Zn actually converge to Z. Okay, so before we assumed this, but now we're going to assume this and assume this. Okay, so then given a positive number, we need to show that these get small enough, that that there's a cutoff so that whenever we go far enough out, the distance between these two is less than d. Then given d, we need show that there exists an n. There exists a cutoff value. Remember, this symbol here means there exists some capital N with going past that point, that capital N point, implies that the Zn's and the Z are very close to each other. Okay? That's just me knowing the definition of what I'm trying to prove. Okay, so now how do I find this capital N? Well, because I'm assuming that these converge, I know that given any positive number d, there exists an n1 and an n2 such that these go. So let's now write that out. Since the real parts of the Zn converge to the real part of Z, there exists some n1 with, and actually I'm going to need to choose like d over 2 or something. but this is me looking ahead. Why am I looking ahead? Because what I have in my mind is z is somewhere, and the zn's are, infinitely many of them are going somewhere in here. And what do I want to do? I'm going to find that the real parts, here's the real part of z, and here's maybe the imaginary part of z over here. Imaginary part of z are on the vertical and horizontal axes. And if I put this within d over 2, and if I put this within d over 2, then I know that my Zn is somewhere in this box, and then a ball of radius d contains that box. Okay? So actually this is important. If you have, and by the way, this d over 2 is actually referring to this length right here. It's d over 2. Same, this d over 2 is this way. But this is really important because that allows us to, from the convergence of the x and y coordinates of these numbers, we can find the convergence of the complex numbers. If you have a little box of radius d over 2, I know that a box doesn't have a radius, but it does. And so this part would be the square root of something complicated. But whatever it is, it's definitely contained in a ball of radius d. Okay, and that's what we needed. So there exists n1 that if you go past n1, then the real part of zn and the real part of z are really close to each other, say less than d over 2. And there exists an n2 with going past n2 implies that the imaginary parts of the zn and the imaginary part of the z are less than d over 2. So these two statements here are the statements of these real parts are inside that ball, and these imaginary parts are inside that ball on the vertical axis. Because of that, I know that the real plus I times the imaginary is somewhere in this cube, and that cube is inside that ball. Okay, so then let capital N equal to the maximum. Just go as far as you need. You need to go far enough so that both of these hold. Then n past that implies that Zn minus c is less than d. But why? Why? Because cube, where this is d over 2, is inside ball of radius d. Namely, that's now radius d, so I make a ball. So that's d. Anyway, that's the end of my proof. Okay, let me let you look at it for a bit. Pause it, maybe. I'm going to talk now, so pause if you don't want to listen to me. The real parts converged and the imaginary parts converged. We assume that. That means that given any d, we can look at d over 2, and we know that if we go far enough past n1, past capital N1, we'll be inside there with the real parts. And past capital N2 will be inside there with the imaginary parts. But that means that our complex number, real plus I times imaginary, is inside that ball. And that ball is definitely, because this cube is in the ball. Anyway, this now is done. This is different from your book. Your book proves it a different way. So your book gives names to the real parts, get the name a sub n. The imaginary parts get the name b sub n. And then they use limit laws. Here's the limit laws, I think. And then they use some proposition 1.6, which they don't say what it is, but it's it must be something about the triangle inequality. And that's fine. Maybe the book's proof makes more sense to you. If so, read it a few times until you can reconstruct the logic of the book's proof. If you prefer, here is a second proof. Well, here's, a proof of the first part that's different from the book. Here's a proof of the second part that's different from the book. Okay,